Either my lectures are very clear or it's very confusing and you don't know where to start to ask, but let's proceed. So this is what I would like to do today is first develop the formalism for the classical Boltzmann equations, specifically in the context of space-time that is expanding. And I just want to mention that, again, this is not something that one often encounters as a PhD student. And so I'm not sure what everybody's background is, but this is something I would have appreciated having some lectures on when I was a student or an early postdoc. So I'm going to do that and then apply it to the leptogenesis scenario that we discussed yesterday, the simplest standard thermal leptogenesis type 1. Then I'm going to discuss how you relate the lepton asymmetry, or more specifically, the B minus L asymmetry to the baryon asymmetry in this context, and you'll have a homework exercise to do. And then, depending on how much time there is, I may or may not discuss the possible implications of the existence of additional lepton number violation in nature at lower scales than the standard thermoleptogenesis scale. So because I've got a lot of material to cover today, I may simply pass on this depending on how much time. But please, by all means, don't hesitate to interrupt me with any questions. So the outline is to start with the classical Boltzmann equations and then the application to the standard thermoleptogenesis, relating B minus L abundance to the baryon asymmetry. And then at least I'll touch on what are some of the open questions for leptogenesis, but depending on how much time there is, may say more or less about this, and of course, invite your questions. So the references are as I discussed yesterday, and so let's proceed with the classical Boltzmann equations. So what I really want to do here is help you see how to derive the Boltzmann equations in the context of an expanding universe. And the second is answer this question: why do we want an equation for the abundance as a function of this Z variable? Remember, the abundance is the ratio of the number density to the entropy density, and the Z variable is the ratio of an appropriate mass to temperature. So why do we use that set of quantities rather than just dN by dt, n dot? And so I hope that will become a little more clear to you as we discuss the derivation of the Boltzmann equations. So as I said yesterday, the Boltzmann equations really involve analyzing in a covariant way the impact of phase space evolution and of some quantity F. And in general, F can be any quantity, but in our context, it's going to be the distribution function for a particle in the early universe. And as I mentioned yesterday, on the left-hand side is the Liouville operator, and on the right-hand side is the collision term. So the picture you should have in mind is that we take a volume of phase space that's three-dimensional in coordinate space and three-dimensional in momentum space. And because the, at least in the FRW universe, the scale factor is increasing with time, that phase space element is increasing. And so one can ask the following question: how do these functions of whatever sort, F, change due to the effect of the expansion of the phase space element, or the evolution of phase space element? And in particular, let's ask how that evolves with the proper time or invariant variable tau. So the Liouville operator is the operator that addresses that question. If there's nothing else going on, we just have a bunch of stuff in a volume of phase space at some initial time, then after an interval tau, proper time, how does that quantity evolve? Now, in addition to just the evolution due to the expanding universe, there are also interactions, collisions, there are decays and inverse decays and annihilations, all of which will lead to either a net inflow of whatever is associated with the quantity F. So let's suppose F is the number density of heavy neutrinos in the early universe, or it's the number density of dark matter. So due to the interactions that those particles have with other objects in the thermal bath, there will be an injection of content of neutrinos or dark matter into the phase space element in addition to the expansion of the phase space volume. And there will also be some probability for an outflow. So the quantity that describes the net change due to inflow and outflow through interactions is called the collision term. And it's sort of a broad term, meaning scattering and decays, inverse decays and annihilations and all those things. So to analyze the complete evolution of F, we need to analyze both the phase space evolution and the interactions, given respectively by the Liouville operator and the collision term. So yesterday I started to talk you through how we analyze the first, the Liouville operator, and I'm going to go over that again a little bit more slowly. So the operator is the derivative with respect to proper time or the invariant variable, and that can be thought of as implicitly a function of x and p. Since phase space is really x and p space, then we really ought to rewrite L in terms of x and p. So I've done so on the right-hand side, and you can see there's a derivative with respect to x and a derivative with respect to p, and we have the corresponding quantities dx by d tau and dp by d tau that multiply. So let's work with this expression. Now the rate of change of the momentum with respect to tau is given in general relativity by minus the Christoffel symbol times the bilinear product of the momentum. And so let's substitute that into the second term inside the red box. So we have in the first term, dx by d tau is just p, and that multiplies d by dx. In the second term, I've substituted the expression for the tau derivative of the momentum. And now I'm going to use the fact that we have spatial isotropy. And this is really tantamount to our FRW universe. And in that case, first of all, the only dependence on spatial coordinate is the time evolution. So in the first term, the only surviving piece is the d by dx naught. And since we take only mu equals to 0, then we have p mu equals to 0, and that's just the energy. So the first term just becomes energy d by dt. In the second term, we take again mu equals to 0. And so we have the derivative with respect to energy and the Christoffel symbol that involves gamma 0 and the product with the spatial components of the four momentum. Now, the exercise that I assigned at the end of the first day in computing the Friedmann equation has you working out the Christoffel symbols. And for the case of gamma 0 ij or jk, it has a really simple form in the FRW universe. It's just proportional to the spatial components of the metric tensor, and the coefficient is the Hubble rate. Okay, so this coefficient here is going to introduce the Hubble rate into our phase space evolution, which is perhaps not surprising. All right, now let's talk about a quantity that we might want to construct from the distribution function, which is f, and in that case, we'll take the number density as an example. So here's our expression for the number density. We integrated over the momentum space part of the phase space and multiply by the degeneracy factor, little g. So let's now take the integral of the Liouville part of the Boltzmann equation. And as I mentioned yesterday, in order to maintain Lorentz covariance, we don't want to take just d3p over E. We really want to take d3p over we want to take d3p over E or something proportional to d3p over E because that is invariant under Booth's. And so this is the appropriate quantity to start with. And so on the right-hand side, I've now taken my expression for the Liouville operator in the spatially isotropic context and substituted it into the integrand for this integral. All right, so here's that expression, and we need to do a little bit of manipulation. So we're going to use a couple of things. Well, first of all, you can see in the first term, there's a cancellation of the e prefactor and the e in the denominator. The integral is a d3p, and so I can just pull the d by dt out. And then you see that I have actually d by dt of the same integral that gives me the number density. So this first term is just going to give me the time derivative of the number density. In the second term, I have to do a little bit more work, and I'm going to use a change of variables from the energy derivative to the momentum derivative, since I'm integrating with respect to momentum. And I'm going to take that and integrate the momentum momentum derivative by parts, rather, in that second term. And I end up with the following expression for this Lorentz invariant integral of the Liouville operator, multiplied by, and there should be a bracket around the 2 pi here, multiplied by g over 2 pi cubed. And so we see that on the right-hand side, we get an n dot, the time derivative of the number density from the first term. And when I do this change of variables and integration by parts on the second term, the sign changes, I have the Hubble rate, and it turns out I get back the integral for the number density times a factor 3. So the right-hand side is really the effect of phase space evolution. N dot plus the effect of the expanding universe is the Hubble rate times the number density. Now, I want to do a little bit more manipulation to variables that turn out to be more convenient. And here's where I'm going to introduce the z variable that I talked about earlier, which is mass over temperature, the abundance, n over the entropy density. And I'm going to use the fact that if I multiply the entropy density by the scale factor, then in the absence of
is it frozen?
Hi, everybody. Sorry about that. My home internet just kicked out on me.
Okay, that's fine.
Yeah.
So could you start from the new slide?
Yes.
Yes,
Let me
yeah.
share my screen again.
Mm.
And this is where we
Yeah.
were, I think.
Yeah. Yes, you can start from this slide.
Number 11.
Right.
So we've compressed down the Liouville operator effect, n dot plus 3hn, to the entropy density times y dot. Now I'm going to do a little bit more manipulation to use this variable z. Okay, let's go here. And there we go. So I'm going to use two facts. I'm going to use the value of the Hubble rate when I take the temperature equal to the mass of the particle, just for normalization. And then it turns out I can rewrite the differential in time as this z variable times 1 over that Hubble rate times dz. And if I do that, then this s times y dot can be rewritten in terms of the entropy density the Hubble rate evaluated at the temperature equals to the mass divided by z, dy by dz. So you can see that it is actually quite convenient to express things in terms of z, because now everything is in terms of a co-moving quantity. There's no time, which is frame dependent, and everything is now expressed in terms of the temperature and the co-moving number density, or the abundance. Now let's talk about the collision term. So the collision term tries to account for various reactions. So let's suppose we have a particle I'll call psi, and it interacts with particles A and B and other stuff, and the interactions lead to a final state with particles I, J plus other stuff. So the integral over the collision term, so I now take G over 2 pi cubed, I take the Lorentz invariant integration measure times the collision term, and I have a really complicated expression on the right-hand side. So what's all this stuff? Well, the d pi's are Lorentz invariant phase space for the various particles. They're just given by d3p over twice the energy. That's the Lorentz invariant phase space with a standard normalization that people use in field theory, and our degeneracy factor for the particle and the 2 pi cubed. So I have one of those for each particle involved. I already had one for psi, and now I have them for everything else. Then, of course, I have an energy momentum conserving delta function. And then I have the amplitude squareds for various interactions. For example, here's the amplitude squared for the particle to scatter out of phase space into the other particles. And that gets multiplied by the distribution function for particle psi, and depending on whether Bose or fermion, 1 plus or minus the distribution particle functions for the final state particles. The second term corresponds to the reverse reaction, scattering in. So we have I plus J plus everything else with distribution functions corresponding to those particles here, scatter to psi plus A plus B plus C, etc. So I have 1 plus or minus F psi and so forth here. This is the scattering in part. And this can all be simplified down to a very simple form, which is if we have time reversal invariance, there's a common matrix element squared and crossing symmetry and other things. We have the Lorentz invariant phase space for the integration. We have the energy momentum conserving delta function. And we have the invariant amplitude squared. And then we have the product of the distribution functions for the incoming particles minus the product of the distribution functions for the final state particles. That's the structure, general structure for a collision term. So hopefully that mess of an expression now makes a little more sense to you if you've never seen it before. Okay, so we've got the two pieces we talked about, the phase space evolution governed by the Liouville operator. That's the stuff here on the left. We have the collision term on the right. And I'm going to divide through by this prefactor S, H, and Z. And I end up with my master expression for the evolution abundance with respect to inverse temperature, Z. It's given by a prefactor and then the collision term integral. So any questions about the ingredients in this derivation?
I'm sorry, but what does the Fi and Fj thing?
Fi and Fj, let me go back to where I have them. These are the distribution functions for the initial and final states. So that would be the Bose distribution function or the Fermi distribution function.
Oh, that determines the plus minus.
Exactly,
right.
That determines the plus minus depending on the statistics that you have.
Okay.
Great, thanks. Are there other questions in this about this? Okay, then let's proceed. and consider a couple of cases. Let's talk about decays. For example, in the case of the leptogenesis process, we'd have a decay of a heavy neutrino into final state particles X and Y. And in the example I talked through yesterday, those particles would be the Higgs and the lepton, or the Higgs star and the anti-lepton. And there's the reverse process where the two particles could find each other and annihilate to make the N. So in that case, what is the formula for the collision term integral? Well, we have the phase space factors, we have the energy momentum conserving delta function, we have the invariant amplitude squared, we have the heavy neutrino distribution function, and then we have the final state particle distributions functions X for Fx and Fy. And it turns out when you do the phase space integrals, and if we assume that the particles X and Y are in thermal equilibrium, this whole complicated integral can boil down to something really simple that involves this second line here. A ratio of the number density of the heavy neutrinos to its equilibrium number density -1 times the equilibrium number density times a ratio of Bessel functions and the decay rate for the heavy neutrino. Okay. So as I discussed yesterday, this expression for that involves the ratio of K1 and K2 times gamma N is the thermally averaged decay rate. And remember, the decay rate at high temperatures is suppressed with respect to lower temperatures, as we saw in that plot that I showed you yesterday. Okay, so this is a kind of term that would appear in a leptogenesis Boltzmann equation that arises from the decay process and the inverse decays. How about annihilation? Now, you might have, for example, neutrino and antineutrino, which are their own antiparticle in the seesaw case, annihilate to the particles X and Y. Or you might have dark matter annihilate to a couple of standard model particles called X and Y. So in that case, here's the formula. We have a phase space factor for each initial neutrino or antineutrino, and for the final state particles, energy momentum conserving delta function. We have the invariant amplitude squared for the annihilation process. We have one factor of the distribution function for each initial state, the N and the N bar. And then we have the distribution functions for the final state particles. And it turns out that if these particles are in thermal equilibrium, excuse me, then the product of their distribution functions can be written as the product of the neutrino equilibrium distribution functions. And so this leads to a very simple formula, which is we have the thermally averaged scattering cross-section times the velocity of the incoming particles times the difference of the number density of the neutrino squared minus the square of its equilibrium distribution. Okay, so that's the formalism. And it's at the end of the day, it's pretty straightforward, but the derivation I think is sort of nice to see where it is that we end up with the Z variable and the use of the abundance, which is really sort of expressing in a very compact way the fact that we have an expanding universe and we're encoding the effect of, excuse me, the scale factor increasing with time. So let's see how this applies to the standard thermoleptogenesis case. Here is, in very general terms, the structure of the Boltzmann equation for the number density of the heavy neutrinos. So on the left-hand side is dy by dz, and on the right-hand side, we have the kinds of terms that I talked about previously. Here's the decay term. Again, it's proportional, can be written as proportional to the difference of the abundance, yn, that we're trying to solve for, and its equilibrium value. And the S would be a process I didn't give you an example for, but that would be scattering. Let's suppose the heavy neutrinos scatter off of particles in the thermal bath. So there's one heavy neutrino involved in that process, so there's one factor of the abundance. And then in principle, there are annihilation terms. And again, as we just discussed, that involves the abundances squared because there are two heavy neutrinos involved in the initial state. Now, the relationship between lepton number and the B minus L asymmetry is something that we are going to use. And remember, the we're going to want the lepton number abundance. That's what's actually produced. And with a few assumptions, that's essentially minus the baryon minus lepton number abundance. Let's suppose we didn't create any heavy neutrinos, any new baryon number density, then YL would just be YB minus L. So at the end of the day, what we want to know is what is the lepton number or the B minus L abundance. And here, the corresponding Boltzmann equation has the following structure. There are two terms. Let's see, I didn't really talk about the first term. The first term we'll discuss in a little bit, but it's proportional to the number density of the neutrinos minus the equilibrium abundance, the decay rate, and the CP violating asymmetry. Now, why does that make sense? It makes sense because if we have an excess or a deficit of the heavy neutrinos compared to their equilibrium abundance, then their decays, if there's an asymmetry, are going to lead to an asymmetry, a net excess of leptons over anti-leptons. And that asymmetry effect, the CP violating effect, is encoded in the little epsilon parameter that we discussed yesterday. So this first term on the right-hand side is called the CP violating source term. The second term is proportional to the B minus L abundance, and it comes with a coefficient called W. It is something that describes what are called washout processes. So these would be, as I discussed yesterday, the kinds of processes where total lepton number can be changed by 1 or 2 units, but there's no CP violation involved. So these processes tend to eliminate any B minus L asymmetry that gets produced by the decay term, the CP violating source. So in the end, there's really a pair of Boltzmann equations we have to solve in the simplest realization. One for the heavy neutrinos, and then and by the way, I am assuming in writing these down, there's no annihilations. So in the example that we discussed yesterday, the annihilation term is actually gone. So there's the heavy neutrino abundance that we have to solve for. And with the presence of CP violation, it sources the B minus L abundance. And then that has to compete against the washout term. So these D, S, and W, the washout terms, are really given by the actual rates, the thermally averaged rates for decays and scattering and washout, divided by the Hubble parameter and Z. That's just because we divided that through when we derived the Boltzmann equations. Okay. And you can go back to the earlier slides and see where that comes from. All right, so here's our basic point. We've got what I call a kind of a wrestling match between the CP violating source, the decays, and the washout processes. So the blue wrestler is the decay, the red wrestler is the washout, and at the end of the day, the answer to whether or not we get a sufficiently large B minus L asymmetry to produce the baryon asymmetry that we observe really depends on the outcome of this wrestling match. All right, so I'm going to show you an example of what these evolutions look like in the case where I neglect the scattering terms and just include decays and inverse decays and the washouts. And this example is taken from a paper where they assumed that there were 3 heavy neutrinos, one of which was much lighter than the other 2, but still heavier than the Davidson-Ibarra bound that we discussed yesterday. In that case, you can actually solve in a semi-analytic way for the B minus L abundance. There are 2 terms. There's a term that if there was an initial value gets exponentially decayed away by the washout term. And then there's the CP violating contribution. This epsilon 1 is that CP violating asymmetry we discussed yesterday. And then there's what's called an efficiency factor for how well that CP violating effect converts to a B minus L asymmetry. And that encodes the effect of the washout. And we can see that in this expression here, the efficiency factor is some integral over the heavy neutrino abundance, its Z derivative, and an exponential that involves decaying exponential of the washout factor. Again, this is all very nice because you can write down these analytic expressions for the solution. There's some other pieces of information here that I don't think I need to talk you through, just specific formulae for the ingredients into the calculation. What I really want to do is show you the plots of what these evolutions of the abundance look like. And so here are two examples in this simple setup. Over on the top left, the vertical axis is the number density, which can be rescaled to be the abundance if I divide by the entropy density. And on the horizontal axis is our Z parameter. The dotted line corresponds to the heavy neutrino equilibrium abundance. The solid line corresponds to the actual abundance and its evolution. And the curve down here is the absolute value of the B minus L abundance. And right here, the heavy neutrino abundance actually becomes its equilibrium value. And at that point, the CP violating source turns off because it's proportional to the difference of these two numbers, yeah? And yet there was already some B minus L abundance, and that starts to decay away after the neutrinos cross their equilibrium value. But then N1 abundance starts to get bigger than the equilibrium value, and it again becomes a non-trivial source for the B minus L abundance. So this decaying B minus L abundance that goes to 0 and then goes negative starts to become non-zero again. And eventually, after all the neutrinos have decayed away, it goes to some constant value of order 10 to the minus 10 in these units. So the bottom plot is a similar plot where the N1s reach their equilibrium abundance much earlier, and you can see that this dip in the B minus L abundance then occurs much earlier, and then the plateau out to a constant value occurs much earlier. These two cases correspond to what are called strong and weak washout, and they are parametrized by a quantity called K, which is the ratio of the decay rate at 0 temperature, so essentially today, to the Hubble rate at the time when the temperature is equal to the heavy neutrino mass. The top plot corresponds to what's called weak washout, and so the N1s reach equilibrium quite a bit later than in the bottom plot where the what's called strong washout regime occurs, where they reach their equilibrium value much earlier, and they tend to stay very close to equilibrium. There's a little bit of a non-trivial difference here, but you can't see it on these plots. Whereas in the weak washout case, it's quite clear that you have a significant difference. Okay, so this is the sort of exercise that one goes through in analyzing the various models for neutrinos at high mass scales in terms of their impact on leptogenesis. And this is just a very simple illustrative example that I think is a very nice way to see how the Boltzmann equations in practice work. So how does this then turn into the baryon asymmetry? After all, it's y sub b that we want, not y sub b minus L. And so this leads to the homework exercise that I'm going to ask you to try to do, to work out how you convert or find the relationship between the B minus L abundance and the baryon asymmetry. So the first step is to recall that in statistical mechanics, when you look at the difference between the number density for a particle K and for its antiparticle, if the difference is very small, that can be expressed in terms of the Boltzmann constant times the degeneracy factor over 6, the temperature squared, and the chemical potential for that species of particle. So we're going to work with chemical potentials, it turns out. The K factor, I'm sorry, it's not the Boltzmann factor. I should have put a B. It was Boltzmann. K is a statistical factor. It's 1 for fermions and 2 for bosons. So strike what I just said. Now, chemical equilibrium or minimization of Gibbs free energy says that if you take the product of the chemical potential for each particle and its charge and sum them all up, that has to be equal to 0. That's the statement of chemical equilibrium. So working out how B minus L gets converted to B is essentially an exercise in chemical equilibrium and charge conservation. The first is the statement that the electroweak sphalerons are in equilibrium. Remember, the sphalerons would in principle change total baryon plus lepton number. That can be converted to a statement about chemical potentials because here's the chemical potential for the quarks, and quarks carry baryon charge of 1/3, so I got to multiply by 3. And then I've got the leptons, which have 1 unit. And if the sphalerons are in equilibrium, there's no net change in the total baryon number, baryon plus lepton number, rather. A second equilibrium condition is something about what are called the QCD, or strong sphalerons. And that's just saying there's no net change in the relative numbers of the left-handed versus the right-handed quarks. So this first term counts in chemical potential units the number of left-handed quarks, and the second and third term count the number of right-handed quarks summed over all generations of quarks. And so if the strong sphalerons are in equilibrium, there's no net what's called chiral charge that is generated, and so that's equal to 0. The third is that, and I don't have an equation for the third and the fourth, the third is that the plasma has no net hypercharge, and the fourth is that all the interactions of the fermions in the Standard Model and the heavy neutrinos are in equilibrium, the so-called Yukawa interactions. And that leads to the following formula. So we have y sub b is equal to a constant times yb minus L, and that constant can be expressed in terms of the number of families of fermions and the number of Higgs doublets in both the numerator and the denominator. So for the Standard Model, if F is equal to 3, so this becomes 28 in the numerator and it becomes 79 in the denominator. So this is a number that's a little bit less than a half, somewhere between a half and a third. So to determine whether or not we have the observed baryon asymmetry, there's no order of magnitude difference between YB minus L and Y sub B. There's just a factor of a third to a half. And so we want to make sure in any calculation in leptogenesis that we get YB minus L to be on the order of 10 to the minus 10, to be in the right ballpark for getting the observed baryon asymmetry. Okay, so that's your homework exercise for this lecture. And now, given the time, I'm going to say a little bit about the open questions, and then we'll start the next lecture, but I'll pause for some question period. So the open questions are the following for leptogenesis. And let's first place standard thermal leptogenesis in the sort of energy scale landscape. Remember, it's up at very high scales, somewhere between 10 to the 9 GeV in the simple realization, that's the Davidson-Ibarra bound, and 10 to the 12 GeV and above. And it involves these heavy neutrinos, which with those masses, no one is ever going to make in the laboratory. So the question is there any way to test this very beautiful idea? And let me just pause and see if anyone has any ideas. How might you test it? Is there any hope? This is where you get to be creative for 1 minute. My experimental friends would love to know how they could test this idea. Well, it's tough. You can't directly test it. The best we can probably do is look for what I call circumstantial evidence for leptogenesis. And let's remind ourselves what are some of the key ingredients for leptogenesis in the standard realization. The first is there has to be lepton number violation. Okay, so there is these days an experimental program to try to look for evidence for lepton number violation. It's called the Search for Neutrinoless Double Beta Decay. And if I had more time, I would tell you about it, or maybe in the question period, I can tell you a little bit about it. And neutrinoless double beta decay, if it's observed, would be smoking gun evidence that there is violation of lepton number in the Lagrangian of the universe, okay? Now, it wouldn't directly test the standard thermal leptogenesis, but it would tell us at least nature has one of the key ingredients for that paradigm. The second is the CP violation. Now, there is a way to look for CP violation in neutrino physics. There is in the neutrino oscillation framework, there is a CP violating parameter called delta that I mentioned yesterday. And so big experiments are being designed to go see if delta is, the sign of delta is non-zero. And so certainly if one were to observe CP violation in neutrino oscillations, you would know that there is at least some hope that there was CP violation at the high scales relevant to leptogenesis. But as I discussed yesterday, that CP violation in neutrino oscillations is not directly connected in general to the CP violation in leptogenesis. So the takeaway message is that the observation of these effects does not guarantee that leptogenesis happened, but it might give us some greater plausibility for leptogenesis. But the converse is also true, that if one does not observe either lepton number violation in neutrino double beta decay or CP violation in neutrino oscillations, that does not preclude standard thermal leptogenesis. And it's all because the mass scale is very high. So it's, you know, depending on how you look at it, either a great theory because it can never be killed, at least in the simplest incarnation, or it's a little disappointing because you can't kill it, depending on your point of view. All right, so there's a longer topic that I would discuss if I had more time that talks about what if there is lepton number violation at lower scales where we can experimentally test it. I will save that for either the break period or discussion. And let's just go to the summary of the key concepts for this lecture. And then depending on how many questions you have, we will start the electroweak baryogenesis lecture either before or after the break. So things you should take away. The first is the Boltzmann equation has two key ingredients, the Liouville operator that describes the phase space evolution and expanding space-time, and the collision term that describes the changes in the distributions due to interactions. I showed you how the resulting Boltzmann equation then applies to the standard thermal leptogenesis case, and that at the end of the day, you know, whether or not leptogenesis works really depends on a competition between CP violation and the decays, excuse me, and these washout processes that change total lepton number but not violate CP. And the open questions for leptogenesis pertain to what I ended with, is it's not directly testable, although one can find circumstantial evidence, but it does lead us to think about, you know, just what is the scale of lepton number violation in nature if it exists? And if it's at high scale versus maybe lower scale, what are the corresponding implications? Okay, so let's stop there and see if anyone has any questions on this, this particular material. Okay, so far I don't see questions.
Can you elaborate more on the work exercises for
the what is it? The baryon symmetry, calculating the baryon symmetry.
On, so let's go
Yes.
back. Do you mean this exercise here?
Right. This slide. I'm not sure what the listed items are.
So the first is, let's go over this. This is the requirement that the electric sphalerons are in equilibrium. And that implies that the sum over all generations of this quantity, which is 3 times the chemical potential for the left-handed quarks and 1 times the chemical potential for the left-handed leptons, summed over generations 1, 2, and 3 is equal to 0.
Oh, so here the items are the conditions needed for the calculation.
These
right?
are the conditions, exactly. So I've given you the ingredients.
Oh,
2 of them are non-trivial, the sphaleron conditions, because we haven't talked in a lot of detail about sphalerons. The third is that the total hypercharge in the plasma of the early universe has to be 0. The universe is simply not charged.
I'm sure.
And the last is that the interactions that involve the Yukawa couplings are in equilibrium. So there's an analogous expression for chemical potentials involving left and right-handed quarks and leptons and Higgses that has to be written down. And so if we take all of these conditions, then you should be able to derive this formula, these formulae in these red boxes.
Okay, now it's clear what I should do. So it's very helpful.
Great, great, thank you. Are there other questions? Seems not. So Pyungwon, why don't I start the next lecture and then we'll break in 10 minutes and continue after the break. Does that sound good?
Okay, yes.
So let me close this. We have actually a pretty long one and it's not clear how much of it I'll actually be able to cover today, but that's maybe good that we get started. And there we go. So we're now going to shift from the leptogenesis idea to the other baryogenesis scenario that I said we would discuss, which is electroweak baryogenesis. And so what I'd like to do in this lecture is explain how electroweak baryogenesis works. It has 2 ingredients, strong first order electroweak phase transition. So I'm going to discuss in some detail the generic features of a first order electroweak phase transition and the viable models and their phenomenology. And then I'm going to touch a little bit on the CP violation and its tests, and of course, always invite your questions. So here's the overview. First, I'll give you an overview of the connection between electroweak phase transition and electroweak baryogenesis. Then I'll talk about how electroweak baryogenesis works, spend quite a bit of time on the generic features of the electroweak phase transition, say a little bit about CP violation, and really depending on how much time we have, and I'm suspecting I won't have enough time to say as much as I'd like, talk about specific model realizations for the electroweak phase transition. And here are a number of references that I encourage you to take a look at. And I am unabashedly self-interested here. A lot of these are papers that I've co-authored. One is a recent paper that I authored last year that I think gives a good pedagogical discussion of the electroweak phase transition and its generic features. So I would encourage you to take a look at that. And I'm actually going to draw on that paper pretty heavily in these lectures. So let's start with the overview. And let's remember our bigger problem, which is to ask how might the baryon asymmetry be connected to the elementary fermion masses. We already discussed the left-hand branch. Now we're going to be discussing the right-hand branch, which is through the Higgs mechanism. In other words, was the baryon asymmetry and the origin of the charged fermion masses and WZ masses, are they connected through the breaking of electroweak symmetry? Let's also put it in the context of our landscape of baryogenesis scenarios with regard to energy scale and time and temperature. So we saw this slide before. Standard thermal epigenesis is up at the high scale. Electroweak baryogenesis, because it involves electroweak symmetry breaking, involves energy scales of order 100 to several hundred GeV. So whereas standard thermal leptogenesis is very difficult to directly test, electroweak baryogenesis is quite accessible to experiments, as we will see. Now, how about in terms of our time and temperature? So here's our landscape, and I've already given you where standard thermal leptogenesis lies. Electroweak baryogenesis, of course, is localized in time and temperature around the era of electroweak symmetry breaking. The universe being 10 to the 15 Kelvin, or about 10 to the minus 11 seconds old. So how about the ingredients? So for electroweak baryogenesis, the out of equilibrium condition is realized through a first order electroweak phase transition. So all that material we discussed yesterday about the behavior of the effective potential at finite temperature is very relevant to this third Sakharov criteria aspect of electroweak baryogenesis. And that, just to remind you again, the idea was if we take a slice in the Higgs potential, remember, can be computed from the effective action, from its tree level part and the quantum corrections. We went through that calculation yesterday. Remember that the effective potential is for momentum independent and spatially independent external fields, the sum of all one particle irreducible diagrams. And that led to this picture here of the possible evolutions of the potential as a function of temperature and the phase diagram. And let me remind you again what the phase diagram is, which I've updated since yesterday's lecture. On the horizontal axis is the Higgs mass, on the vertical axis is the temperature. This yellow line is the line for which, if the Higgs were sufficiently light, you would cool down and go through a first order phase transition. But there is a so-called critical point or critical Higgs mass above which the transition is crossover. And the value of that critical point, as we discussed yesterday, has been obtained from these lattice calculations of 70 to 80 GeV. So the first order phase transition that we need for electroweak baryogenesis can't happen in the standard model simply because the Higgs is too heavy. It could have. And in fact, in the earlier days when we didn't know how heavy the Higgs was, people did consider the possibility of electroweak baryogenesis in the standard model, you know, when the Higgs was thought to be maybe 40, 50 GeV. But now we know it's too heavy. And so what we really need is new physics at the several hundred GeV scale or so. And so if that's there, we can ask, what is the corresponding phase diagram? So how do we get a first order phase transition by adding something new to the standard model? Well, there are really three ways that this can happen that come out of what we discussed yesterday. There can be new thermal loop effects that involve new bosonic degrees of freedom beyond those in the standard model that create the barrier. It turns out there can also be a somewhat of a shift in the standard model effect at finite temperature due to a zero temperature effect in the Coleman-Weinberg potential. That's a little bit more subtle, so I won't be discussing it. And the third possibility, which is also very interesting, is that once you introduce a new bosonic degree of freedom to the standard model, it can also get a vacuum expectation value and therefore change the entire vacuum structure at tree level of the theory. And that turns out to open up some new pathways for a first order electroweak phase transition. So in this lecture, I'm going to be talking about both of these examples, and I'm not going to spend any time really on the Coleman-Weinberg potential effect, but you can read about it in the paper that I pointed you to, that I posted at the end of last year. So let's talk about how electroweak baryogenesis works, and this may take us, it's really only takes a few minutes. I think we can do that before the break. And we start with our picture here, which of course describes how the Higgs potential evolves with energy. And the point was that if we're in a first order history, once the temperature cools below the critical temperature, then the universe makes a transition to the broken phase vacuum. And the way that works in practice is that the universe starts in the symmetric phase, and then it nucleates bubbles of broken electroweak symmetry in the background of unbroken electroweak symmetry. The bubbles eventually expand, collide, coalesce, and fill the entire observable universe with the broken phase. Now, as we discussed, if the Higgs is too heavy, we don't have this, so we need to add something to the standard model to get the bubble nucleation, and that is the new bosonic degrees of freedom. And in particular, it's effective to look for new scalar particles. And so, as I said, we're going to talk about the effect of new scalars in terms of loop effects and a tree-level barrier. Assuming that they do the job to give us a first-order electroweak phase transition, there are actually a number of interesting consequences. One of which is the viability, possible viability of electroweak baryogenesis. Another is that the collisions of those bubbles can lead to the generation of gravity waves. A third possibility is that those new scalar particles might themselves contribute to the dark matter. And the fourth is that we might actually be able to see the evidence for these particles either directly or indirectly through experiments in high energy collisions. So let's assume we have a first order electroweak phase transition that leads to bubble nucleation. And so here are bubbles of broken electroweak symmetry. They nucleate in the background of unbroken symmetry. The CP violation, where does that come in? It comes in at the interactions of particles at the bubble walls. So let's suppose that there's some slight difference between particle and antiparticle interactions at the bubble walls. That will lead to a particle asymmetry. And in particular, it has to be a left-handed particle asymmetry. And the reason for that, we'll come to in a minute, come to right now, is that those left-handed asymmetry will then cause the electroweak sphalerons to make more baryons than antibaryons. We're going to discuss the sphaleron effect tomorrow in a lot of detail, but that's the basic idea. So we've got to have a CP violating interaction at the bubble wall that causes the sphalerons to make baryons. And it turns out that CP violation in the standard model doesn't work. It's too feeble. So it has to be CP violation beyond the standard model. Let's assume that that exists as well. So we have the new ingredient of the bubble nucleation from new scalars, or new Higgses, as I sometimes call them, and the beyond the standard model CP violation. That makes a asymmetry, a baryon asymmetry outside the bubbles. That asymmetry then diffuses into the interior of the bubbles as they are expanding. Now, that is not good enough to ensure that we have a baryon asymmetry in our broken phase. Because if the sphalerons are still active inside the bubbles, they can wash out the baryon asymmetry. It's a little like it's analogous to the washout effect in leptogenesis. So somehow the sphaleron effect has to be really suppressed or quenched inside the bubbles. And that leads to the requirement that the transition be a strong transition, very abrupt, so that the sphalerons are active outside and make the baryons. And then once the baryons diffuse inside the bubbles, the strong transition turns off the sphalerons or quenches them, and we are left with the baryon asymmetry that is frozen inside the bubbles, the broken phase. So the ingredients, as we said, are new scalars to get a first order electroweak phase transition. It has to be a strong transition in the way that we will define in more detail tomorrow. And there has to be new CP violation to bias the sphalerons into making a net baryon asymmetry. Okay, so open research problems that we're going to discuss in the rest of the lecture are: what new particles and interactions do we have to add to the standard model to make the electroweak scenario viable, the phase transition and the new CP violation? How might we test these possibilities in a variety of different probes? And a third, I think, equally compelling challenge, particularly for people who are much more theoretically inclined, is how reliably can we compute the effects on the phase transition and the baryon asymmetry in generation. So let's stop there. I know we're supposed to have a break. I'm happy to stay online for a couple of minutes and take questions now, if you'd like, or if you're really exhausted, we can just break and resume in 30 minutes. So Kyungwon, what would you
Yes.
like me to do?
Yes, let me just ask if there are some questions. Any questions? Any questions from the audience about today's lecture or the previous lectures? Is everything crystal clear to the students?
I hope so. And if not, I would really appreciate hearing some questions. So maybe you can use the next 30 minutes to think of what your questions are.
Yes, yes. Okay, I don't see any question immediately. So maybe we can have a 30 minutes break and meet at 11 a.m. Thank you, Mike.
Sounds good. We'll see you all shortly.
Mm. Oh, hello, everybody. Now, the second lecture by Professor Ramsey Musolf. Please.
Right. Okay. Welcome back, everybody. Before I proceed, let me just ask if there are any questions that came up over the last 30 minutes. Happy to take a little time now. Okay. So then I will proceed and let us now pick up where we left off. So as I said, there were three broad open research problems that we address with electroweak baryogenesis. What is the new physics that we need to make it work? How can we test it experimentally? And how reliably can we compute the effects in the early universe? So what I want to do now is kind of give you, for the electroweak phase transition part, a very broad brushstroke picture of generic features of the new interactions and the corresponding possible connections with phenomenology. We will discuss in more detail tomorrow the issues about doing calculations. But today I'm going to focus on generic features in the phenomenology. And there are two sort of generic features that I want to address. One is, what is the mass scale that is allowed for the new particles to have in order to make a first order electroweak phase transition possible? And the second is, it must somehow talk to the Higgs boson. And so that means there will be some changes in the Higgs boson properties. How big must those changes be in order to see a first order electroweak phase transition? And therefore, how precisely do we have to measure Higgs boson properties to test this possibility? So let's start then with the new particles and interactions. And I'm going to go way back to this very beautiful paper by Steven Weinberg on symmetry breaking at finite temperature. And in that paper, there is a very provocative discussion, very provocative for me, and also I think very illustrative for how we may think about the patterns of symmetry breaking in the early universe. Now, what Weinberg was considering in the example that this figure portrays, and I'll tell you in just a minute what's in it, was not the spontaneous breaking of a gauge symmetry, but the spontaneous breaking of global symmetries. There was a question that came up yesterday about whether our effective potential ideas could apply to global as well as local symmetries, and they certainly can. And here's an example from Weinberg's paper. So Weinberg asked the following question. Let's consider a different theory called ON cross ON. And in that theory, there are two Higgses, one called phi 1 that corresponds to one of the gauge groups and the other called phi 2. And when the symmetry is spontaneously broken, then the neutral components of phi 1 and phi 2 will become the Goldstone bosons of the spontaneously broken symmetry, as the Higgs would, were it not for the local symmetry. And so what Weinberg asked was, depending on the values of the masses of these two Goldstone bosons, the phi 1 mass and the phi 2 mass, he called them eta and chi, and I'm going to call them phi 1 and phi 2, what might be the symmetry breaking patterns that could have existed in the early universe? Let's start with the point here, point 1 in his diagram, where there's a certain value for the two masses, phi 1 mass and phi 2 mass. And what he says is that the universe cools with the stipulation that the masses of the two bosons be these m eta and m chi, then the universe, sorry, my cursor is not doing too well, would follow this trajectory where as the universe cooled, the symmetry group would break down to what's called group B. So we start in group A with a full ON cross ON gauge symmetry, and we break down to group B where one of the factors gets broken to a lower symmetry, ON minus 1. That's very analogous to what happens in the standard model. We start with SU2 left cross U1 Y, that would be A, and as the universe cools and the Higgs gets a vacuum expectation value, we break down to U1 of electromagnetism. That would be B. That's what we're used to thinking about. But Weinberg says there were other possibilities. One is that for certain values of the masses of the two Goldstone bosons, you never would have the full asymmetry. You would just simply stay in phase B. A third possibility for this choice of the masses over here, the initial symmetry might be ON minus 1 cross ON. And as the universe cools, it actually goes to phase A with a greater symmetry for a period of time. And then it breaks to phase B, where the lower symmetry is a different broken symmetry. Or you could start in point 4, where the symmetry group is phase D, ON minus 1 cross ON minus 1. As the universe cools, it gets more symmetric, phase C, even more symmetric, phase A, and then less symmetric, phase B, and so forth. So there are a number of possible trajectories of the symmetry breaking in the early universe in this very simple setup of two ON groups, and it all is governed by the parameters in the Lagrangian, the M eta and M chi. So that leads to the following question. If we are going to add a new scalar field to the standard model that we hope will give a first order electroweak phase transition, it might be that the symmetry breaking will still be like in the standard model pattern. We start with a higher symmetry and we break to a lower symmetry. But it's equally likely that we would have other symmetry breaking patterns by adding the extra scalar. And what Weinberg's example here points out is that we're very used to thinking in the simplest possible terms, but nature didn't necessarily have to be that way once we expand the scalar sector of the universe. So here's a way to think about that in our context. Let's now look at a possible plot of the effective potential as a function of both the Higgs and some new scalar particle I called phi. On the axes here, on this axis here is the Higgs direction. On this axis here is the phi direction, what I call the beyond the standard model scalar. This is how the potential might look. Over here, the minimum is along the Higgs direction. That's what we call the Higgs phase. But there are also possible minima along the phi direction. So in the standard model, of course, the breaking of the symmetry starts from the symmetric phase to the Higgs phase. That we call a one-step transition in this context. But if we think in Weinberg's sort of framework, there's no reason why we had to go directly to the Higgs phase once we have another scalar field in the problem. Maybe we could have gone to the phi phase first and then to the Higgs phase. Who knows? It all depends on the parameters of the theory. So the point is that the extrema in the energy surface or the effective potential can evolve differently as the temperature evolves, and that opens up the possibility of a much richer array of symmetry breaking patterns than we have in the standard model alone. So we ought to be a little bit more creative about how we think about it. So I want to analyze what the possible consequences are in a very simple and rather generic setup. And the other piece of information to think about in this context is that nature has actually handed us an energy scale that therefore sets the scale for all other aspects of this problem. And in particular, when we try to connect the new scalars to searches in collider physics. So I call it TEW sets a scale for colliders, but it also sets a scale just for, in general, these rich pattern of symmetry breaking. So what is TEW? Well, let's start with the standard model effective potential in the high T limit, the leading order, what's called the leading order high temperature effective theory, which we discussed yesterday. That's the first box here. And as you recall, the leading temperature dependence has a quadratic term in H and a term that depends on the temperature squared and the zero temperature mass squared. And then there's the quartic coupling of the Higgs and other higher order terms that are less important at high temperature. Okay. And for this potential, neglecting the cubic term, we would have in the standard model a second order transition to the broken phase. Now let's review what the formula for T naught squared is. T naught squared is proportional to the Higgs self-coupling lambda plus some loop effects that are not important for this discussion. Then in the denominator, there's a dependence on the couplings of all the particles that interact with the Higgs. The Higgs itself, that's lambda, the SU2 gauge boson, the hypercharged gauge bosons, the top quarks, and then other contributions that are smaller because the couplings are much smaller. And then it's proportional to the Higgs vacuum expectation value squared. So you can see that the temperature T naught that defines when the symmetry is broken is partly set by the electroweak scale, but it's also partly set by all the other couplings in the theory. So it really behooves us to think of it as an independent parameter. And that number, it turns out, is not so different from the weak scale. It's about 140 GeV, but depending on the values of the top quark, Yukawa coupling, the Higgs self-coupling, it could have been significantly different. So I'm going to call that scale T electroweak. That is a number that nature has handed us. Okay, it exists in the Higgs potential if we believe the leading order effect is the standard model. So now we want to ask, how could beyond the standard model of physics add the barrier to give us a first order electroweak phase transition, a barrier at finite temperature? And I'm going to talk about this in the context of adding this new scalar field phi that interacts with Higgs via what's called the Higgs portal. Many of you have undoubtedly heard about Higgs portal, but let me just remind you what a portal is. A portal is a way that something that is not part of our standard model universe talks to the standard model, okay? And so you might call that beyond the standard model world the hidden sector, and the portal is the way it talks to the standard model. So the Higgs portal is that these new particles talk to the standard model by interacting with the Higgs. So at the renormalizable level, there are different kinds of Higgs portal interactions that one can write down, and they lead to the following set of interesting possibilities for the trajectory, the history of symmetry breaking in the early universe. So let's start over on the lower left. We have the Higgs direction, and now we have a direction in field space associated with the neutral component of the phi. It is possible that the transition still proceeds from the origin, the symmetric phase, directly to the broken phase in the Higgs direction. That transition, as we've learned in the standard model, is a crossover. So we want to make it first order and strongly first order. Well, the relevant Higgs portal interaction that we introduced to do that involves, okay, my cursor is disappearing on me here, a product of Higgs squared and phi squared. It's a dimension 4 operator, and it comes with a coefficient I call A2. And there is a loop effect from this interaction that could lead to this transition being strongly first order, or lead it to be first order. Now let's look in the middle. A second possibility is that the universe starts at the symmetric phase at the origin, but instead of going to the Higgs phase, it first goes through at a temperature T phi to a phase involving a vacuum expectation value for the phi particle. And it lives there for a little while until it becomes energetically favorable for the universe to move from the phi phase to the Higgs phase. This is an example of that so-called two-step phase transition. And again, this Higgs portal interaction is the relevant interaction such that the transition from the phi phase to the Higgs phase would be first order. A third possibility is that in one step, we break the symmetry to a phase where both the Higgs and the phi have non-zero vacuum expectation values. And in this case, there's a different Higgs portal interaction that is very relevant that involves h squared and 1 power of the field, phi. So it's dimension 3, and its coefficient A1 is a dimensionful, carries mass dimension effect. This would be a tree level effect, just as this in the middle would be a tree level effect, whereas the first would be a loop effect. And now we can ask the following question: what are the consequences in terms of the parameters of the theory, the mass of the phi particle, and the strength of its coupling to the Higgs that would enable any one of these to lead to a strong first order transition to the Higgs phase? So let's start with the first two, with this Higgs portal operator h squared phi squared. It turns out there are very simple arguments that use this number, t electroweak, and the requirement that we have a first order electroweak phase transition to derive a bound, an upper bound on the mass of the phi particle. And it turns out that mass is somewhere in the 350 to 700 GeV range. It can't be too heavy, is the takeaway message. Let's show how that works in these two cases. Let's start with the first, the loop effect. And let's go back to what we discussed yesterday, which are these cubic terms in the thermal potential that come from the Daisy resummation. As you recall, the relevant effect is proportional, it's got a negative sign, it's proportional to the temperature over 12 pi. And now the contribution from the phi particle interacting with the Higgs comes in as its thermal mass cubed. Here's the formula for the thermal mass cubed. It's a square root, it's the 3/2 power rather, of the following quantities. There is a tree level contribution to the mass. It comes from a parameter in the theory called B2. Let's just call that the tree level mass. There is a contribution to the mass at zero temperature that comes from the Higgs getting a vacuum expectation value. It comes with the Higgs portal coupling, A2. And then there is the thermal mass contribution that we discussed yesterday, proportional to T squared and the same Higgs portal coupling. So three contributions, a tree level contribution, a field dependent contribution, and a thermal contribution. Let's now imagine that somehow nature conspired such that the values of B2 and A2 lead to a cancellation between these first two terms when the temperature is around the electroweak temperature. What would be the consequences? Well, there are two consequences. Let's look at the first in the upper box on the lower part of the left. The change in the potential around that temperature then would be proportional to T electroweak over 12 pi with a minus sign. And then I would have all the stuff left over inside this square bracket. Only the field dependent mass contribution would survive. And that would lead to a dependence that is h cubed, a cubic term, which is just what we want for a first order transition. The second consequence is I can now ask what is the corresponding value of the mass at zero temperature once I impose this requirement. And I can translate those requirements into this expression here for the mass squared at zero temperature. It depends on the Higgs portal coupling, the electroweak temperature squared, and the Higgs vacuum expectation value squared. That's coming from the field dependent mass part here. How big is this number for the mass? Well, if A2 is in the range where perturbation theory is valid, then this number is at max maybe 350 GeV. So for this mechanism to work, the phi particle just can't be too heavy. All right, so that's the first case. Let's try the second case, which is analogous, and I'll come to why 700 GeV appears in just a minute. Now we want to ask about the following possibility, the following history. We start at high temperature at the origin, and at some temperature T1, the universe first makes a transition to the phi phase, and then at a lower temperature, T2, it makes the transition to the Higgs phase. So what we want is, first of all, a tree level barrier between these two phases here, so that this transition is first order. And we want the temperature T1 to be greater than T2 so that we start up here and then go through the barrier to get to the Higgs phase. And we want T2 to be around the electroweak temperature because that's the temperature of electroweak symmetry breaking that nature has handed us. So what are the consequences of this possibility? Well, to analyze it, we need to look at the effective potential along the phi direction only, where the Higgs value is 0. And in that case, it has the following simple formula. There is a quartic interaction that you can write down, and I call the coefficient B4. There is a quadratic interaction, and like in the Higgs sector, it comes with a negative sign so that the symmetry can be broken at sufficiently low temperature along the T1 direction. And then there's a thermal loop contribution, the thermal mass, as we discussed. It comes from the B4 as well as the Higgs portal interaction. So what we want is for this term, which is positive at sufficiently high temperature, to become negative at some temperature T1, and we want that temperature T1 to be larger than T2, so the universe first goes here and then it goes here. What are the consequences of that? Well, the consequences, you can work out a very simple logic. It takes a few lines. For the 0 temperature mass is that it has to be smaller than the formula in this box here. It depends on the Higgs portal coupling, the electroweak temperature, and the quartic coupling of the phi particle to itself. And again, if these couplings A2 and B4 are in the range of perturbation theory, then the mass bound is remarkably about the same as in our first example, less than about 350 GeV. So if we're going to have a first order phase transition in any one of these two trajectories, the mass can't be too heavy. Now, there are reasons to sort of relax the mass bound a little bit, which I'm not going to go into. You know, perturbation theory has some limits of validity. There are other effects that we didn't take into account. And so to be a little bit cautious, we'll add a factor of 2 to this mass bound, but it's still not arbitrarily heavy. If it's 700 GeV, that is still light enough that in either the LHC experiments or future high energy experiments, you ought to be able to see, that ought to be able to directly produce the phi particle. So when I say the electroweak phase transition is a collider target, that's part of what I mean. So let's talk about how well you might test these two scenarios. The first thing to say is that, again, I already said the factor of 2. The second thing to say is that the Large Hadron Collider has already excluded particles that carry QCD charge, scalar particles up to much higher mass than 700 GeV. So if phi is going to do the job, it has to carry no QCD charge, it has to be a singlet. The third bullet is that the typical cross sections for producing it, as we'll see, are on the order of 1 to several hundred femtobarns at the Large Hadron Collider and up to order 25 picobarns at a future high energy 100 TeV proton-proton collider. And then there will be some consequences for precision Higgs studies, which we'll discuss. Here's just a quick example of the possible electroweak pair production. Let's suppose that phi is part of an electroweak multiplet, and you were to produce it in a future E plus E minus collision. Let's take, for example, the center mass energy that people are thinking about for the CEPC in China or the FCCEE at CERN, you know, at the Chi bar energy of 340 GeV. If you were taking the mass of the phi particle to be 100 GeV, then with the expected integrated luminosity, you might expect to get you know, several 100,000 events. On the other hand, if the particle is much heavier, you can't make it directly at these lower energy E plus E minus machines. It might take something like click. You could still get a lot of events, but the moral of the story is, of course, you need the center of mass energy to do that. Okay. In proton-proton collisions, this is very doable. If it's the Large Hadron Collider, again, several thousand to tens of thousands of events are possible even at the upper end of the mass range. And 100 TeV PP collider, you could take the upper end of the mass range and get maybe close to 1 million events. So, so it's eminently doable in a future proton-proton collider. Now let's talk about the phase transition as it interfaces with Higgs boson properties. And I kind of like this little cartoon because it says we have the standard model Higgs, and if there's anything else around, like our new scalar that's interacting with it, it's going to tickle the Higgs a little bit in a very, maybe almost imperceptible way. And that's where we need precision studies of the Higgs boson to see the effect. So what are the kinds of observables that one might use in looking at the Higgs boson properties to probe the possibility of a new scalar being around to do the first order phase transition? Well, one is the rate for the Higgs to decay to 2 photons. That's a very important one. The second is the strength for the Higgs boson to couple to all standard model particles. The third is the way it couples to itself. And the fourth, which we may discuss a little later, are new decay modes for the Higgs boson called exotic decays. I'm going to focus here on the diphoton decay rate, which is particularly interesting for the h squared phi squared barrier producing interaction if phi is part of an electroweak multiplet, meaning it's got charged partners as well as the neutral component. Why is this important? Well, it's important because the Higgs portal interaction that's relevant for the phase transition is the same interaction that would lead to these loop contributions for the Higgs to decay to 2 photons. So here's our h squared phi squared interaction where one of the h's gets a vacuum expectation value so you don't see it. The coupling here is A2. Here are the charge partners of the neutral phi, and they allow an interaction with the photons. So looking for this effect might be a way to work backwards to probe this barrier, in addition to making the phi particles directly. So how precisely might we have to measure the Higgs diphoton decay rate to do that? Here's an example plot. It's a very simple calculation that illustrates the precision needed. What's plotted here is the following. On the horizontal axis is the mass of the phi. On the vertical axis is the relative change in the Higgs diphoton decay rate. So the numerator is the change and the denominator is the standard model value. The curves correspond to different values of the Higgs portal coupling, this A2 parameter ranging in the 1 to 2.5 range. And the first thing to note is that for these positive choices, which is what we need for the barrier, there's always a decrease in the Higgs diphoton decay rate. So if you were to observe an increase in the Higgs diphoton decay rate, that would argue against this particular kind of scenario. On the other hand, a decrease would argue in favor of it. Now, how precisely would you have to measure it? Well, it really depends on the mass and the coupling. If we take a coupling to be order 1 and the mass is around 200 GeV, then the change would be about a 5% reduction in the Higgs diphoton decay rate. And if you go to higher and higher masses, it gets down to around 1% or so. How well do we think future colliders might do in probing for this effect? Well, here's an example taken from a talk I heard this summer that indicates the relative precision from various possible future colliders. Dark green is the high luminosity LHC. The sort of moderate green is if you take the high luminosity LHC and add various incarnations of the International Linear Collider. This red is if you take the high lumi LHC and add CLIC. The bright green is the high lumi LHC plus the CEPC. And the orange is the high lumi LHC plus the FCC program with either EE or EEEH and HH, hadron-hadron. The bar chart at the down below corresponds to the precision on the coupling. So to get the precision on the rate, you have to essentially take a factor 2. So here for the high lumi LHC, it says maybe 5, 1, 2, 3, 4, maybe 10, between 7 and 10%, since we take this and multiply by 2. For the CEPC, the statement is that the high lumi LHC plus the CEPC could get us down to around 2%. So that's getting us over here in this range here. And the long-term future with an FCC program gets us way down here. So well into the precision range that we would be able to definitively probe this possibility. So Higgs diphoton is very interesting. Now let's talk about the second and third possible ways that we can study the properties of the Higgs boson in precision measurements, the signal strengths and the self-coupling. And here, instead of being the h squared phi squared barrier that we've discussed, the relevant scenario is the third one that we haven't discussed in detail yet, the h squared phi barrier. Let me remind you what that is. That's in our set of possibilities here, where the universe starts at high temperature in the symmetric phase, and as the universe cools, the symmetry breaks to a phase where both the fields have vacuum expectation values. And here, the h squared phi interaction can lead to a barrier that is crossed when this transition occurs. It's a zero temperature tree level effect, just like this one in the middle is a zero temperature tree level effect, whereas the first one we discussed was a thermal loop effect. So for the phase transition, this is very interesting. And at zero temperature, the consequence of having a VEV for phi and for H is that the Higgs boson and the phi neutral component mix to make two mass eigenstates that are mixtures. And that effect is what we can look for in precision measurements. Okay, so H phi mixing is a way to probe the h squared phi barrier effect. There's another consequence, which is now we can produce the phi particle in the same way that we produce the Higgs boson. We can produce it singly because of the mixing with the Higgs. Anything that produces a Higgs will also produce the phi. Okay, so I've added that to the list here. It's not really precision measurement, but it should go on our list. Now, what sets the scale for how precisely we have to look for these effects of mixing that show up in the signal strength or the self-coupling or in single phi production? Well, as we will discuss tomorrow for baryogenesis, we want to make sure that the interaction doesn't just give us a first order phase transition, but the sufficiently strong one to prevent the washing out of baryon number after the transition has started to occur. Another consequence, which we won't have time to discuss, is that you would like it to produce observable gravity waves. That would be nice, but I'm going to rely on this first one of not only having a first order phase transition, but requiring it that it be sufficiently strong to preserve the baryon asymmetry after it is made. And it turns out one can work out in a very straightforward way. We won't do it in the class because of time. That leads to a very simple requirement on the ratio of the Higgs portal coupling A1 to the electroweak temperature and the Higgs self-coupling. Throw in a factor of 2, and that has to be greater than order 1. Okay, so you can see the statement that the scale is set by T electroweak, and in this case, the Higgs self-coupling, and we need to have A1 sufficiently large compared to their product. Okay. What does that imply about the mixing angle? Well, it turns out that if this ratio is order 1 or larger, then the absolute value of the mixing angle is greater than about 0.01, so 1% mixing. That's pretty small, but it's not arbitrarily small. It can't be arbitrarily small. If we then take the value 0.01 and translate it into a statement on the shift in the coupling of the Higgs to itself, that's about 0.3% or larger. So these set sort of the scale for how precisely we need to measure Higgs properties in order to probe this h squared phi barrier effect. Okay, so it is really, again, a real target for experiment. And I'm not going to talk much about single phi production unless somebody asks me in question, but I did want to at least introduce for you the idea that there is a real target for measuring these properties. Okay, so that's all I want to say about the sort of general features of the phase transition. If we want to get a first order phase transition, and in particular, if we want it to be sufficiently strong, the mass of the new phi particle can't be too heavy and the way it couples to the standard model Higgs can't be too small. And we can make that very quantitative using those simple symmetry breaking patterns that we discussed that involve either the thermal loop effect or the tree level barriers. So now I want to say a little bit about the beyond the standard model CP violation. And this, it turns out, is actually theoretically a much more challenging problem for computation. So we're not going to have a lot of time to talk about that. I'll allude to it a little bit, but I'm not going to spend a lot of time actually going through the technical details, because it would just, I'd like to leave you with the big picture ideas. So let's go back to our electric baryogenesis, and now we're going to concentrate on the CP violation. And so as we said, it has to be CP violation beyond the standard model. And then the theoretical problem is how to calculate those asymmetries that get produced through the CP violating interactions at the bubble walls. So let's look at a bubble. Here's one bubble. And remember, inside the bubble, we have new scalar fields around to generate the first order phase transition. They can have vacuum expectation values, as can the Higgs, and everything else around could interact with the new particle. And in particular, the new particle itself might have CP violating interactions with the vacuum expectation value of the Higgs or with other particles. So the generation of a CP violating asymmetry outside the bubble actually depends not only on the size of it, depends not only on the CP violation here, but also actually two other pieces of physics. So there's really a competition between three processes. There's CP violation. CP violation leads to a difference between the rates for particle and antiparticle interactions. Okay. The second is the physics of chemical equilibration, meaning if I produce more A particles than anti-A particles, then if A is interacting with something else, then that asymmetry in A could get transferred to particles B and C, for example. Okay, so some of the asymmetry will transfer to other species. The third ingredient is the physics of diffusion. So the stuff is interacting, it's scattering outside the bubble, and it's diffusing ahead of the bubble wall. And the more effectively it can diffuse, the more effectively the sphalerons outside the bubble can turn it into a baryon asymmetry. So we have CP violation, chemical equilibration, and diffusion. How do we quantitatively work out the competition? Well, before we already saw in the case of leptogenesis what we had to do to work out the results of a competition. We had to derive a set of Boltzmann equations. So for this problem, there's an analogous set of Boltzmann equations that one has to derive, and they're a little more complicated. And the reason, which I didn't put on this slide, but let me tell you, the reason why it's more complicated is that outside the bubbles, the particles do not get any contribution to their masses from the Higgs vacuum expectation value. But inside the bubble, the Higgs VEV contributes to the mass. So as the particles are moving in the presence of these expanding bubbles, their masses are changing. So we have to derive a set of Boltzmann equations that are appropriate for particles propagating at the same time that their masses are evolving with space-time. And that is a very interesting and open theoretical problem to do that as rigorously as possible. So we have made some steps along the way and tried to work out what the resulting CP violating asymmetries are. But I just want you to be aware that this is an interesting area for future research if you get interested. But let's take an example of how this works. And I'm going to use the minimal supersymmetric standard model, for which there are about 30 coupled Boltzmann equations that include this mass varying effect that one has to write down to completely analyze the CP violating asymmetry. And so I'm not going to write down the formulae for you. It's too complicated for an overview lecture like this, but I am going to use a sort of graphic sort of depiction that my current colleague, Bjorn Garbrecht, who's in Munich. He was a former postdoc when I was in Wisconsin. And he came up with this around the time we were in Wisconsin. He said, the Boltzmann equations are really trying to describe something like the London Underground. Okay, so over here, we start with a CP violation. And it involves some particle species. And that particle species can interact with other particles and have the transfer of number densities through chemical equilibration. It can have the physics of diffusion. And there are lots of different pathways to get the CP violating effect ultimately to the place where it makes a baryon asymmetry. Okay, these ingredients include Yukawa interactions, supersymmetric gauge interactions, the strong and the weak sphalerons, and so forth. Those all are sort of depicted by these pathways in the London Underground, and the Boltzmann equations encode that mathematically. So we solve the Boltzmann equations. It's a non-trivial problem. And what we get from that are particle profiles, number densities, as a function of their distance from the exterior of the bubble to the interior of the bubble. Let me show you what one looks like. And then this is some old work we did, but it still is a relevant, very interesting sort of example. So what's shown here? Well, on the horizontal axis is the distance relative to the bubble wall. The bubble wall is taken at 0. The bubble interior is in the positive area here. So you might think of the 0 as sitting right here, and the bubble interior is in the positive direction, and the negative direction is the bubble exterior. These colored curves correspond to the number densities of different particle species as a function of the distance from the bubble wall. For example, the pink is the left-handed quarks, the green is the left-handed leptons, and the red is the sum of the two, the total number density of left-handed fermions as a function of the distance from the bubble wall. Now, the sphalerons like to have this number density of left-handed fermions as large as possible to make the baryon asymmetry. So in the end, it's really this what's called diffusion tail of left-handed fermions outside or ahead of the advancing bubble that really ultimately determines whether or not we get the right baryon asymmetry. And the value of that tail is really the result of solving this complicated set of coupled Boltzmann equations. Now, there would be nothing without the CP violation. So the CP violation is really active right at the bubble wall where the value of the Higgs field is changing, it turns out. And so you can think of that as kind of a jolt or a kick that nature gives to this whole system of equations. It's the source that then has to find its way to the baryon asymmetry through this diffusion tail that comes from solving Boltzmann equations. So it's critical to be able to test how large the CP violating effect is. And that leads to the last topic that I'll discuss in this lecture, which is search for beyond the standard model CP violation using electric dipole moments. Now, I don't know why this went on 2 lines here. I'm bothered by this. Yeah, this better be. There we go. Looks a little better. Okay. All right, so first of all, the scale of experiment that electric dipole moments comprise is very small compared to a collider physics experiment. Here on the left is a photo of the apparatus for a search for the electric dipole moment of the electron. It fits literally on a tabletop. Here on the right is a photograph of 2 experimentalists at the Paul Scherrer Institute who are trying to look for the neutron electric dipole moment, and the apparatus sits inside this sort of tube thing behind them here. So it's a somewhat bigger table, okay? And both experiments are looking for the same kind of effect, one on the electron, one on the neutron. So let's remind ourselves what an electric dipole moment is and why it's interesting for this particular physics. Of course, in classical, you know what an electric dipole moment is in classical electrodynamics. It's just a product of a charge times the separation. That's not interesting for our purposes. What's interesting for our purposes is the electric dipole moment of a quantum system. And in that case, you know, by virtue of the Wigner-Eckart theorem, that the electric dipole moment of, say, an electron or a neutron has to be proportional to its spin. And we'll call the coefficient proportionality the electric dipole moment. The way you would look for the effect is to put that spinning object in the presence of an electric field. If it has a non-zero electric dipole moment, then it will precess around the electric field. And that precession will be associated with a frequency that depends on the energy of interaction divided by Planck's constant. Okay? So in effect, what the experimentalists look for in those two pictures is this precession effect. And the fact that they don't see it puts a limit, an upper limit on the magnitude of the electric dipole moment. Now, why is this interesting for CP violation? Okay, so let's look at the way an experiment is actually done. They put the spinning object in the presence of a magnetic and electric field. Of course, these objects have a magnetic field, and so they're precessing around the magnetic field. If you turn on an electric field, then the precession frequency will change due to the contribution from the interaction of the electric field and the electric dipole moment. And that contribution will be given by this frequency formula that I showed you before. Now, this frequency or this energy or this Hamiltonian, effectively in the numerator, is odd under time reversal. And therefore, by the CPT theorem, it would reflect CP violation. So let's time reverse this experiment. In that case, the spin would reverse, but the electric field would not. Let's forget about the magnetic field effect here. Let's just look at the effect on the EDM frequency, and you can see that the sign of the frequency changes. So it's time reversal odd. Of course, in a real experiment, you can't reverse time. And so what EDM experiments actually rely on is the fact that this interaction also violates parity. So if we reverse the electric field, that's a parity transformation, the sign of the EDM effect also changes, whereas the magnetic frequency does not. So the way experiments are actually done is they reverse, they put on electric field and they flip the direction, and they look for a modulation of the precession frequency due to this modulating electric field. And so far, nobody has seen anything. So there are limits, and somehow my slides here are, somehow the formatting is not great. Hopefully this will do the right thing here. So these are the current limits. The three most stringent systems where electric dipole moments have been looked for: the mercury atom, the thorium oxide molecule, which is used to look for the electric dipole moment of the electron, and the neutron. These are limits in units of e centimeters. They are limits that are still much larger than what you would expect from the standard model CKM-CP violation, but there's nothing that precludes the beyond the standard model CP violation from being just right around the corner. So just to give you a sort of a intuition for what the meaning of this scale of EDM limit is, I like this example that an experimental colleague of mine gave me. She said, look, if the neutron were the size of the Earth and it had a charge of 1 unit of electric charge of the electron, then this limit on the neutron electric dipole moment would, in a classical setup, be equivalent to allowing the separation of a +1 and -1 charge to be no larger than about 1/4 of a millimeter. So it's really impressive. And so that's how, you might think about it when you tell your friends. And by the way, there are lots of efforts going on around the world to try to improve limits on the electric dipole moments of various systems, including some discussion that a colleague of ours, Professor Samrat-Zidis in Korea, about looking for the electric dipole moment of the proton, which is a very interesting and exciting possibility. And again, my PowerPoint sort of setup here is failing me. I'm sorry about that. I just can't live with this. I don't know why. Let me just save that. So this is where we're at and where we'll go. And these future experiments are trying to improve the sensitivity by about a factor of 100. What does that mean for baryogenesis? Well, let's look at the possibility just in the minimal supersymmetric standard model, which I used before. This plot illustrates the sensitivity. On the horizontal axis is one of the relevant supersymmetric particle masses. On the vertical axis is the sign of the CP violating phase. The details aren't important to you. What's important is that to get the baryon asymmetry right, you'd have to lie on top of this bright green curve. Now, the current neutron EDM limit is up here. Improving by factor 10 would get you down here, so it would start to probe some of this parameter space. And it turns out a factor 100, which is around the goal for the next generation experiments, could conclusively test it. On the other hand, the electron is racing against the neutron, and the electron is winning so far. The current electric dipole moment of the electron is already down here. It excludes almost everything above this, this line right here. So there's a little room left with some theoretical caveat that I can mention in these remarks, but you can see just how powerful the electric dipole moment searches are. So here's a slide that an experimental colleague, a fellow named Mike Pendlebury, who's now deceased, but he was one of the big players in the neutron electric dipole moment searches, has used to sort of show the comparison of theory and experiment. So this dotted line here is the historical evolution of the limit on the neutron electric dipole moment. The blobs correspond to various theoretical predictions. Roughly speaking, where we would have to be to get the baryon asymmetry right is given by this blob here. The present EDM limit is around here. The future EDM limits are down here. And the question is whether that could really conclusively probe electroweak baryogenesis models. What we think is that in supersymmetry, minimal version, you might be able to do it. But on the other hand, there are lots of creative ways to get around these theoretical, these experimental limits, and that's a topic for research and discussion. Okay. So I think I've come to the end of my time, and as I expected, I would not be able to discuss many of the model illustrations, and so let me go to the big summary here. Where is my big summary? Yes. So what are the key concepts that I hope you got in this somewhat longer lecture on electric baryogenesis? The first is just the basic idea of how it works. The second, as we discussed, are the generic features of how we get a first order electroweak phase transition and how that connects with possible experimental tests. The third, as we just discussed, was the CP violation needed and how that can be probed with electric dipole moments. And what I expected I wouldn't have time to discuss and didn't are very concrete model illustrations in various contexts. So we won't do that. So tomorrow, the last two topics move a little bit away from the phenomenology and model building side, more toward the more theoretical side. We're going to discuss about sphalerons, and then we're going to discuss about open issues in what I call the electroweak baryogenesis frontier that includes calculating the rate for nucleating these bubbles and some questions about how well we can use perturbation. So I will stop there and let's see if anyone has any questions.
Oh, Michael, thank you very much. Any questions from the audience?
I have a question.
Yes.
So could you elaborate a bit more about the setting Boltzmann equation for the expanding bubbles, like particularly regarding how we deal with the change in the mass of the particles as the particle got belong to the bubbles?
Yes, so that's a great question, and that's a really tough problem of how to analyze Green's functions in the presence of a space-time varying mass. So what we have to do is at every point in space-time, we have to re-diagonalize the mass matrix. Let's say we have two particles, okay? And when you do that carefully, it's like redefining the input parameters in the Lagrangian. And that change, because it's space-time dependent, introduces a term in the Boltzmann equations that can lead to the CP violating effect. Now, the formal way to do that requires at least one full lecture. What we use is something that is appropriate for field theory out of equilibrium. It is called the closed time path formulation of quantum field theory. Maybe I'll add a slide or two tomorrow at the last lecture to sort of say something about it. But it is, and it's something we could use you know, in analyzing finite temperature as well. So remember when we did finite temperature yesterday, that was called the imaginary time formalism. Closed time path is sometimes called the real time formulation, okay? Now, to say much more than that really requires a full lecture, and that's, it's a great and very interesting problem, and I can give you some references maybe tomorrow to some of the things that I've written on it and other people have. And I'll try to maybe say a thing or two in the discussion section. But it boils down to saying in the Lagrangian, we're changing the mass as a function of space. And so when we compute the Green's function, which solves the corresponding Green's function equation, it introduces new terms into the equations of motion for the fields. And that affects the Green's function evolution.
Okay, I'll be waiting for that. Thank you.
Thank you.
So any other questions? Okay, I have a few questions.
Sure.
Okay. So first of all, you talked about classical Boltzmann equation. And do you think that the quantum mechanical Boltzmann equation is any importance in this kind of
Well, in fact, yes. You know, we really, actually, these Boltzmann equations that involve the space-time varying mass, in some sense, are quantum Boltzmann equations.
Yes.
And similarly, even in leptogenesis, a more sort of rigorous and careful way to encode the loop effects that are important for the CP violating asymmetry, since they're loop effects, these are quantum effects. That can be done through quantum Boltzmann equations. And in both cases, it's this closed time path or Schwinger-Keldysh formulation that is useful. You just have to be careful when you write down a classical Boltzmann equation, because there are effects that you might not think of when you think in terms of classical physics that can be decisive when you come into the quantum Boltzmann equations. So the short answer is yes.
Okay. And in the specific example for CP violation for baryogenesis, you mentioned MSSM. So is this electric baryogenesis in MSSM still viable, considering all the collider searches for supersymmetric particles?
So the short answer is the following. The phase transition part is not viable. So, but the CP violating sector still is. And so if you would expand the MSSM to something that includes gauge singlets, like the next to minimal supersymmetric standard model, the scalar singlets can drive the phase transition, and all the CP violation that you had in the MSSM can still be there to give rise to the CP violating effect.
Right, okay.
So I think of the MSSM as kind of a subset of a larger supersymmetric setup where the calculation of the CP violating effect would include what I just showed you earlier. There are actually other CP violating phases that arise as well once you include the singlets. But so it's an excellent question.
Okay. And could you go to the page 64 of your slide?
64.
Yeah, this is a very nice general classification of the possible phase transitions. So for example, so your argument for these three different cases are very general and generic. Okay. So
Yeah,
for
that was the,
example,
yeah, go ahead.
So for example, if you have the third case, H scale phi term, then the dominant effect is a tree-level effect, not from the loop effect.
Typically,
Or,
that's true, right?
yeah, and in this case, if you have H scale phi type interaction only, then you cannot have a two-step phase transition like in the middle graph.
Well, it's actually a good question. There's one other possibility, which is in the middle one, you first go here, and then instead of going all the way to 0, you
Yes.
go part way. So it's really like a mixture of these two effects. But in that case, you know, the barrier here is coming from this. And so it's just as simple to, you know, and then the fact that you're away from the origin is a consequence of this. But your trajectory in field space climbs over a barrier here, and the dominant contribution to the barrier is coming from this interaction here. So to be simple enough in my classification, I didn't put these two together, although you can, but it's really, you know, the first orderness is really driven by this effect here, as far as I understand it.
So this part of your lecture is based on your paper last year in December?
Correct.
Okay, I'll take a look at the paper and maybe have more questions tomorrow also.
Sure,
Okay,
great.
So
be aware that it's in revision. There will be a longer version if you really have an interest in it, but what's on the archive now is fine.
Okay. Yeah. So are there any questions from the audience? Okay. So today I forwarded the lecture notes by Michael to all of you. So please take a look at this lecture notes and make your own question to Michael tomorrow. Okay. Thank you very much, Michael, and